Hello, let's talk about osmosis. And osmosis is very similar to diffusion. In fact, we can define osmosis as equal to the diffusion of small solvent molecules. And the prime solvent we're going to be looking at is going to be H2O through a semi-permeable membrane. And what exactly do we mean by diffusion? So diffusion is this process where there's a net motion from high to low concentration. So there's sort of net movement from high to low. And the thing about diffusion is that it's normally just pretty dumb. So that is to say, the molecules don't know that they're in a region of high or low concentration. They're just moving around at random. And because there's more molecules in a high concentration region than a low, there's just more of a chance that they'll move away from the high region and kind of fill in the low concentration region. So the only solvent we're going to really look at in this chapter under osmosis is water. And it does occur in some other solvents, but it certainly helps if they're very small. Now, what do we mean by semi-permeable membrane? So that's actually kind of an interesting thing. What exactly do we mean here? We can think about it in many ways as imagine a piece of fabric where we've sort of poked pins through it and there's little itty bitty holes. So think of something for now as just it's got very small holes in, kind of like a tennis racket, so the tennis balls will bounce off of it, but if you drop, say, BBs through a tennis racket, they would fall right through. So the semi-permeable membrane, we're just going to think of something that can allow passage of small things but not large things. Okay, so that gets us on to the topic of osmotic pressure. So what exactly do we mean by osmotic pressure? And, well, we have to kind of examine what will happen if we take two solutions and we separate them with a semi-permeable membrane. So I'm going to draw that red dotted line there, and my solvent molecules I'm going to draw in blue. And I'm going to make them pretty small to the point where you could see they could easily fit through the holes in the membrane. And on one side, I'm just going to have pure solvent, and I'm just going to make that the right-hand side, I guess, so make that pure water. And on the other side, I'm going to have a solution, and I'm going to have an aqueous solution. And so that just means that water is the solvent. And let me go ahead and draw these in, and I'll speed this up. But my solution is going to be composed of solutes that are going to be relatively large compared to the solvent itself. So here we go. And we're going to go ahead and have these at the same level. So I'll just draw a yellow line there. That would be the meniscus, right? That would be the level that the solutions are at. So that's where we're starting off at. So what we're going to see here is two things. We're going to see essentially diffusion through the semi-permeable membrane if possible. So we know diffusion is a process that takes you from high to low concentration. So if we look at the green solution, if we look at the green, solute molecules here, they would like to diffuse over to the other side. Now, the problem with that is that there's a barrier in the way, and these molecules are so large they simply can't fit through there. So what we also have going on here are the blue solvent molecules, and we can see there's more on the right than the left. So if you like, the concentration of solvent, of water, is bigger on the right than the left. And just through sheer chance, they can move through the holes. And since there's so many more on the right than the left, there's just more likelihood they'll go from right to left than left to right. So that is osmosis. That is the idea that you see a net flow of these small solvent molecules through the barrier here. So this is the osmotic flow, and it's really just coming from the fact that there's just more water molecules on one side than the other. So the interesting thing about it, though, is if you look in terms of concentration of solute, this right-hand side has got a low solute concentration. Okay, and the left-hand side has a high solute concentration. And it's sometimes helpful to look in terms of the water concentration or the solvent concentration. And we know that if we've got a lot of solute on the left, we've got very little water on the left, but correspondingly, we've got a lot more water on the right. So you can see it's sort of diffusion of the solvent from the high to the low concentration side, as opposed to the solute that can't fit through that semi-permeable membrane. So let me go ahead and write the semi-permeable membrane on here. So semi-permeable membrane. Okay, so what does osmotic pressure have to do with any of this? Well, if we draw the after view, so I'm basically just going to redraw this And osmosis is actually kind of pretty slow, so I'm not going to go ahead and do this in real time. If water is moving from the right-hand side to the left-hand side, that means that the left-hand side water level is going to increase, and correspondingly it's going to decrease on the right-hand side. And what's kind of interesting about all of this is that that extra solution on the left-hand side is applying what we call a hydrostatic pressure. So the weight of that extra column is pushing down, and so that's the weight, right, the force due to gravity, and it's sort of opposing the net osmotic flow. So the net osmotic flow, right, is from right to left according to my blue arrow. So this height of the left-hand side can actually get quite high. So in trees, of course, this can go up to like 30, 40, 50 meters or so. So that's how sap gets up to the very top of the tree. But sometimes we just really don't want to wait for it to kind of build up on one side. So what we're going to go ahead and do is define the osmotic pressure as the extra pressure that we've got to apply and squeeze down on this side to stop the flow of osmosis. So let me go ahead and draw another slide quickly and go through this. So we can stop the flow of osmosis by applying this pressure here called the osmotic pressure. So here we go. Here's our barrier right here. And here's our height on the right and our height on the left. And we've got a high solute concentration on the left-hand side. And we've got a low solvent concentration on the right hand side. So we know that water would have a tendency to do a flow from one side to the other. And what we're going to do, right, is we're going to apply an additional pressure, of course, the osmotic pressure, to kind of oppose this flow. So this is pi, and this represents the extra pressure that we've got to apply in order to stop osmosis, so we can kind of prevent this flow from happening by applying this osmotic pressure. We won't worry about it too much. Normally this is open to the air, so there's atmospheric pressure pushing down here and in here. So this is the additional pressure that we have to apply in order to stop osmosis. And this has already been a long video, so in the next lecture I'll go ahead and talk about how you can calculate that osmotic pressure and how it's a colligative property, so it's actually related to the concentration of the solute. So stay tuned and watch the next lecture for details.